Perfect. So we are now ready to go to the next talk of this session. The speaker is Eleny from Stanford, and he's talking about thin compactification and relative fundamental classes. Eleny.
Okay, so thank you so much for the invitation to give this virtual talk. I hope that the next talk will be, next meeting of Pacific Rim will be actually in person. So let's see. So let me start with some motivation and results. This is based on joint work with Tom Parker. And it's about a classical problem as we have in symplectic geometry. We have just some, let's say we just have some moduli space. Wait, it's not moving. What's happening? Sorry, just a second. Why is it not working? Before it worked, right?
Yes, it did actually.
But you cannot see me scrolling to the next page. Oh no. Okay, I'll stop sharing and I'll start sharing again.
Okay,
sorry.
Yeah, no problem. Maybe we can use the arrow.
Right. Sorry, just a second. Somehow it stopped sharing. Just apologize. It worked perfectly. Okay. Let's see. Okay, maybe now you can see. All right, I don't know, it worked before, but okay, all right. So these are the motivation and the results. This is based on joint work with Tom Parker, as I was saying. And the classical situation is that we have some moduli space M that over some parameter space. Okay, so that this just means that we have a Fredholm map between two separable Banach manifolds. Okay, and then classically we compactify this to get some compactification M bar over the same parameter space, where this just means that we have an extension of this projection to a proper and continuous map. And what we're going to assume to begin with is that we have transversality strata-wise, which is to say simply that if you look at the restrictions, so here is a picture, if you want, of this compactification. The red stuff is what we've added to compactify and to get M bar over the same parameter space. And let's say we have this compactification is stratified for simplicity. And let's assume that we have transversality strata-wise, which is just to say that this extension, if you restrict it to each strata, you get a Fredholm map. Okay, Fredholm map between two separable Banach manifolds. And we also assume that the boundary strata are codimension at least 2. And I should have said, we are also assuming that this projection, or if you want its restriction to each strata, it's sufficiently differentiable so that Sarsmail theorem applies. So then Sarsmail theorem will imply that, first of all, the generic fiber of the uncompactified moduli space is the manifold, but also the generic fiber of the compactified one is compact, of course, because the map is proper, but it's a manifold away from a codimension 2 set. And furthermore, let's see, I guess I have a question. Oh, why doesn't it show? Oh, I see. Just talk being recorded. Okay, so it's a manifold away from a codimension 2 set, and we get a similar condition for the compactification over a generic path in the base. So if you have a generic path in the base, then you've got a manifold with boundary between one end and the other end. So that's the standard situation. That's a classical situation in symplectic geometry or gauge theory, and that's how one gets invariants. If you have this condition, then you can extract invariant. So the result I would like to discuss today is joint work with Tom Parker, and I want the same conditions here that we have usually from Sarsmail imply that we get not just invariants numbers, but we actually get some classes, a virtual fundamental class. So the result is as follows. Under the assumptions star, the same assumptions over here, it doesn't matter how we got them. Maybe we got them from Sarsmail theorem, but however we got these conditions that we know that the generic fiber is compact and it's a manifold away from codimension 2 and a similar condition over a generic path, then the generic fiber will have a fundamental class in some homology theory. Okay, I'll say which homology theory shortly, but it will have a fundamental class in some homology theory. It's not in singular homology. And furthermore, there is a unique extension that associates to every parameter in the base a class called the virtual fundamental class in the homology of the fiber, compactified fiber, for every point, or for every parameter, in such a way so it's consistent in paths, which is to say that if you have a path gamma from P to Q, like in the picture over here, if we had a path, well, I didn't draw the path, but let me draw the path. If we had a path here, gamma from P to Q, then over any path from P to Q, the fundamental class at one end, a fundamental class at P is the same as the virtual fundamental class at Q in the homology of the cobordism between compactified cobordism between P and Q. Okay? And of course, using this, we'll get invariants by pairing with cohomology classes as the usual way. But this gives us more. It gives us this collection of classes, this collection of virtual fundamental classes associated to every single parameter. And of course, our main motivation for this is the virtual fundamental class in Gromov-Witten theory. But this is a purely, if you want, topological result. These are purely topological conditions that we have this condition star. It doesn't matter how we got to them, and then the result here is just purely topological. Any questions so far? If you have questions, please type something in the chat, and then I will address them. So that is the result. So now I also wanted to mention that our result, of course, because our motivation was coming from the virtual fundamental class in Gromov-Witten theory and how much of the classical results can be used to obtain, stronger results in terms of homology classes. Our result is also compatible with the classical definition of Gromov-Witten invariants using, for example, pseudo-cycles. It's also compatible with the definition using cut-down moduli spaces. I'll state precisely this compatibility towards the end of the talk. And it's also compatible with Pardon's definition of the virtual fundamental class using implicit atlases, which is to say that all these constructions give the same answer in a very specific form. When all are, when all of them work, let me put it this way, right? If you have such a situation, then you also have an implicit atlas, then the two constructions are the same. And the other thing I would like to mention is that there is a very simple criteria that ensures that these conditions star are satisfied beyond Jussard's Mail theorem. And then other properties, I'll mention more properties towards the end, but just to begin with, this actually shows that the invariants constructed are really independent of the compactification. In other words, if you have two compactifications of the same moduli space that both satisfy this condition, because our result only applies when you have this, the generic fiber is a manifold away from codimension 2 and the same over a generic path. But if you have two such compactification with this property and you've got, say, a map between these two compactification, then the push forward of the virtual fundamental class constructed using the first compactification is the same as the virtual fundamental class constructed using the second compactification. So really, to some extent, this virtual fundamental class does not depend on the compactification used. And another property that is very useful is that having a homology class rather than numbers. For example, if you have, or for whatever reason you can find an open and closed subset of your moduli space. Is it frozen? I think it froze again. What's happening? Very strange that it keeps freezing. Yes, it froze again.
It's not that if you click, sometimes if you click on the screen, if you take a zoom action, then just try at least clicking on the screen and then just, does that work or not?
No, it's frozen.
No, okay, that's no problem then.
This is really annoying. Let's see. I guess maybe because I've been, sorry, I'm stopped sharing it and I have to share again. share a screen. I really apologize, but it's really very strange.
Oh, that's okay.
Maybe I should have shared my maybe I should have shared in a different fashion, or maybe I need to click on the screen more often. All right, so yes, right now it's moving. So let's see. So one of the advantages is that if we, for example, as I was saying, if you can decompose, if you have an open and closed subset of the moduli space, then a fundamental class, of course, or any homology class will decompose as a contribution coming from this open and closed subset and a contribution coming from its complement. And a motivation for using that, for example, if you have a curve which is what's called super rigid, in other words, if the curve together with all its multiple covers don't have deformations, don't deform to other in the normal directions, that gives rise, the curve together with its multiple covers gives rise to an open and closed subset of the usual moduli space of holomorphic maps. And so in particular, it has a well-defined local contribution to the Gromov-Witten invariants, which can be written as some integral of some obstruction bundle over the virtual fundamental class. So that was one of our motivations for looking at this. Okay, any questions so far? Besides the annoying feature of having to turn on and off the sharing. Let's see. So, right. So which homology theory, right? So let me go and present that. So for which homology theory this works? So first of all, the singular homology, if you wanted to get this kind of result for singular homology, that is hopeless. A better thing is to use what are called Cech-like homology theories, or these are called sometimes second type 2 homology theories. You have to give up something, but you'll also gain something. So these are not going to be homotopy invariant, but you gain two important properties. One of them is called relative homeomorphism, and the other one is called continuity, and that I'll present shortly. And in fact, there is more than just one theory. So first of all, there are at least three such theories we could use, and natural maps between them. So the first theory over here is what's called the dual to the, it is the dual to the Cech cohomology. I hope we are all familiar with the Cech cohomology, and this is the dual space. But then there is a refinement called Cech homology and a map to the dual to the Cech cohomology. The Cech homology, so these are all theories developed in the 70s and 80s, very familiar even to people that work in dynamical systems. The problem with Cech homology is that it's not a homology theory per se. It doesn't satisfy all the Eilenberg-Steroid axioms. It doesn't satisfy the exact sequence of a pair unless you work maybe with Q coefficients or with compact coefficients. But there is a refinement of it called Steroid homology, which satisfies all the Eilenberg Steroid axioms plus several other axioms that are very useful for our purposes. And of course, there are natural maps between these homology theories. The other thing I should mention, not only that they're not homotopy invariant, but they're not really defined for all spaces. The best setup for our purposes is in the category of locally compact Hausdorff spaces. All my spaces are Hausdorff, and all my maps are continuous. But these homology theories, if you want to work and push forward homology classes, the maps have to be not just continuous but also proper. Okay, it's very important. You won't be able, so you have to work with locally compact Hausdorff spaces and proper continuous maps. For example, those which extend continuously to a compactification will have this property. And maybe I should just mention that over Q and for compact metric spaces, which is mostly, the moduli spaces we're mostly interested in, have this are compact and metric spaces. All these theories are equal by Milner's theorem. So this actually becomes isomorphism if you work over Q and for compact metric spaces. Okay. Now, what are the properties that allow us to talk about a fundamental class and a virtual fundamental class in Steroid homology? So the first property is that if you have a closed pair in this category, of course, of locally compact Hausdorff spaces, if you have a closed pair, then you have an exact sequence, which is the usual sequence, almost the usual sequence of a pair, except that here you have a restriction to the open set, which is the complement of the closed set, with the complement x minus a, in this sequence, in this exact sequence. And this is where the relative homeomorphism property appears. So relative homeomorphism property of steroid homology says that if you want at the steroid homology of a pair, of a closed pair, it only depends on the difference x minus a. It does not depend on how a sits in x. Okay, so there is this relative homeomorphism property where you can basically, these are what are called single space theories. You don't really need to work with pairs. You can just work with the difference. And of course, this is false for singular homology. And the second property that is important for our purposes is that any orientable d-dimensional manifold has a fundamental class in this steroid homology based on what's called locally finite infinite chains. Okay, and again, our manifolds here are not necessarily compact, but they have to be Hausdorff, as I said. And as an example, the top dimensional steroid homology of the open ball is actually Z. Okay, but of course, you know, as a world of warning, if you want to push forward, for example, the fundamental class, you need to work with proper maps, such as those which extend to compactification. Any questions about this? All right. So let's see. So this motivates the introduction of a notion of what we call Syn compactifications. So here we're going to have a d-dimensional manifold as before, and we're going to call a compactification of it thin if the singular locus, which is the complement, maybe I'll draw a picture, right? So we have some manifold, and then we're going to compactify by adding some singular locus, that's S. You know, it doesn't matter how badly, how terrible we're going to add a singular locus S. The only thing that matters is that it's a closed subset, of course, because I mean, that's what we need to know. But it's also codimension 2 homologically, which is to say that its steroid homology vanishes in dimension at least d minus 2. Okay? Because if we have this, then this exact sequence over here will tell us if you take your A to be the singular set, and if you take your M to be the compactification, then this exact sequence will tell us that we have a natural isomorphism between the d-dimensional, the top dimensional homology class of the manifold, where the fundamental class lives by property 2, and the d-dimensional homology of the compactification. And in particular, the fundamental class of M has a unique extension as a homology class in the homology of the compactification, and it's really independent of compactification. All these groups are naturally isomorphic to each other. They don't really depend on the compactification. And of course, a basic example of that is if your manifold has at least dimension 2, then the one-point compactification satisfies this property automatically. It's thin, and it's in fact the smallest compactification that satisfies this property. Now, of course, in applications where we want to apply this, not many maps we care about extend to the one-point compactification. So usually in the applications, what we need to do, we need to find some compactification which is big enough so the maps we care about, maybe like evaluation map or stabilization map or whatever other maps we may care about, extend continuously to this compactification. But it's also small enough so that when you compactify, you add things which are only codimension 2. So the compactification is what we call thin. Okay, so that's if you want the game. And then of course there are some criteria that ensure this happens. So a simple criteria that ensure this holds is when the singular locus is always closed, but when the singular locus can be covered by countably many images of manifolds where n alpha are manifolds of codimension at least 2. The manifolds here have to be metrizable, or if you want equivalently sigma compact. And the maps, right, so they're images of this manifold, the maps are either continuous and locally injective or locally Lipschitz, okay? Then, if that is the case, then the singular locus is homologically codimension 2, and in particular, this compactification is a thin compactification, and so all the results before apply. So there are two main examples for this in applications. One of them is when the complement, the singular locus, is stratified by codimension to manifolds, then property A applies over here. And then it, it's stratified, so you've got it covered by codimension to manifolds, and the map is locally injective. And then the second example is when these maps are C1, then the property B applies, and that's the case when you talk about pseudo-cycles. But again, just as a word of warning, we need some condition, such as A or B on the maps, simply because otherwise there is a counterexample of a space filling curve, which increases dimension, right? The image, its image has more dimension than its domain. So we do need, when we talk about covering with images of maps, we do need some sort of condition beyond continuity to ensure that the dimension of the image stays smaller, stays codimension too. Any questions? All right, so let's see, and then of course there is a parallel discussion for what we call Syn Cobortism or thinly compactified Cobortism, where I have here a picture over a path, and we have a manifold, so we have a Cobortism which has been compactified, and the main property, as you would guess, of this thinly compactified Cobortism is that the fundamental class of the compactification at one end is the same as the fundamental class of the compactification at the other end of the Cobortism in the homology, in the steroid homology of the Cobortism, and it follows the same way using the same arguments as before. Okay, and so with this, we can now are ready to extend this to families, where we have some moduli space, more generally some moduli space. Well, here is over just a path, but we can do it over a more general parameter space. All my pictures look the same, but we've got some moduli space and got compactified by adding perhaps some horrible singular set, but it's so that the compactification is proper and continuous. Okay, but of course the horrible singular set, the condition is that it's codimension too in each fiber. I mean, in the generic. I mean, if I wrote exactly the condition that the generic fiber has been compactified with codimension to something with codimension too. So let's see. So to extend this to the family, the way we're going to proceed is as follows. Generically, so we had some conditions before. Let me even our assumptions. The precise assumptions were the generic fiber was compact and a manifold away from codimension 2, and similarly we had in a generic path. And so if we want to extend this to families, then what we're going to do, we already know that the generic fiber has a fundamental class in steroid homology. We're going to take that fundamental class in steroid homology, push it to Cech homology, and then use what's called continuity property of Cech homology to extend it to a fundamental class, to a virtual fundamental class for every fiber. Okay, so here is the important property of Cech homology, that if you have an inverse system of compact Hausdorff spaces, then the homology, Cech homology of the limit is the limit of the Cech homology. Okay. Now again, this is completely false for singular homology, so there is no hope using a singular homology for this. Here is a place where we're having going to the compactification. It's important beyond the fact that working with proper maps, we need to work with proper maps. So being able to extend them to a compactification will make them proper. Extending them continuously to compactification will make them proper. Here is another place where working with compact sets is useful. We do work here with Cech homology, or if you want, we can pass to rational coefficients. Steroid homology satisfies a modified continuity property. It doesn't have this property. There is something called the derived lim1 term, that this is not always an isomorphism. But over Q it is. So anyway, either pass to rational coefficients or map from steroid homology. If you want to work with Z coefficients, map from steroid homology to this rational, to usual Cech homology, and use the this continuity property of Cech homology. So here is now the situation. more precisely, we're going to assume that we have some moduli problem over some family. Okay, it doesn't matter how we got it. We have some separable Banach manifold over. So we have a Fredholm map between two separable Banach manifolds. One of them we're going to think of it as our moduli space. The other one we're going to think of it as a parameter space. And so we just want this map to be Fredholm and relatively orientable. Okay, so in particular, the generic fiber will be a manifold. And then a thin compactification of this family, will simply be a proper continuous extension of this map to a space which will just require to be metrizable, and which has the following property that the generic fiber is a thin compactification of the generic fiber of the original family. And then over a generic path, M bar gamma, it's a Syn Cobortism. Okay, so that if you want, it's a definition that formalizes the situation and specifies the conditions. It's basically the same condition started we had before. The only extra condition is that we're going to ask this to be metrizable, so we don't get into further trouble, unnecessary trouble. And of course, typical example is the situation where this compactification minus the top stratum or whatever we wanted, right? The moduli space we wanted with, it's stratified by codimension to manifolds, or more generally covered by such, as in the criteria before. Okay, so these are our typical examples where we have such a thinly compactified family, and specifically the main result is that any such thinly compactified family has a unique, we call it relative fundamental class, that associates to every single point in the parameter space a fundamental class in Cech homology of, oops, it shouldn't say X, sorry. It should say in the Cech homology of the fiber, M P bar, such that it satisfies two properties. One is called the regularity property, this virtual fundamental class is the same as the actual fundamental class for the generic fiber. Remember, the generic fiber is a thin compactification, so its fundamental class extends uniquely to this thin compactification, and that's what this means. This is what this regularity property requires, that it's the same class as the one obtained from the usual fundamental class extended to the compactification. And the other condition is that it's consistent in paths. In other words, the virtual fundamental class associated to P is the same as the virtual fundamental class associated to Q in the Cech homology of the compactified moduli space over gamma for any path gamma from P to Q. So those are the two conditions. Any questions so far? I don't see any questions. If you have some questions, oh, okay, yes, I see now, maybe. Yeah, so M, what's going to happen? So let's see. So what's happening is that M here, so I got a question. So M, the total space M, it's a separable Banach manifold, and because we're asking that this map be Fredholm, right? Then Sart's theorem will, and of course I should have said sufficiently differentiable, Sart's theorem will imply that the generic fiber of this family will actually be a d-dimensional manifold, and this condition that it's relatively orientable will also mean that it's actually, if you fix a relative orientation, and I should have said this, it's relatively orientable and oriented. This actually means that the generic fiber is a d-dimensional, so this is a Fredholm of index D. The generic fiber will be a d-dimensional oriented manifold. So yeah, so in particular, we'll have a fundamental class in steroid homology, and that extends uniquely to the thin compactification, any thin compactification, in particular this thin compactification. All right, other questions? All right, so that's if you want just a topological result. Now, what are the examples? So let me first give you some examples, some finite dimensional examples that actually show that this notion of fundamental class, a virtual fundamental class, actually depends on the parameter space. Okay, depends exactly how we consider the situation. Okay. And so these are the two examples to consider. Suppose we have an elliptic vibration. So, you know, this is just maybe a 4-dimensional manifold. The generic fiber is a torus. It's a 4-dimensional manifold over, say, a sphere. The generic fiber is a torus, but then you have some what's called multiple fibers, where you have fibers around wrap with a multiplicity. Then you know, you can consider this, of course, as such a thinly compactified family. It hasn't, I mean, you don't actually need to compactify it. All the fibers are actually manifolds, compact manifolds. But of course, if you were to look at the virtual fundamental class, what you look in the definition of the virtual fundamental class here, associated to this multiple fiber, would actually be a multiple of its actual fundamental class. Okay, so the way this virtual fundamental class is obtained, you just look at the fundamental class of a generic fiber, and then you extend it by continuity. So you'll get a multiple. Oops, sorry. You'll get a multiple of this fundamental class. So that's one of the observations. And the second one is a typical example of a blow up. If you blow up a point, then you get an exceptional divisor. You can also think of this as a thinly compactified family. I mean, it hasn't really been compactified, but anyway, the generic fiber here is a point. And so the fundamental class, the virtual fundamental class will be 0-dimensional. And the fiber, you know, the exceptional fiber, the fiber over the blow-up point, is higher dimensional. And it has a fundamental class, but that's not what its virtual fundamental class is. It's going to be 0-dimensional. So it really depends on what kind of parameter space you use. And then we have a condition when if you have a virtual fundamental class over some parameter space, under what kind of conditions, if you enlarge the parameter space, you get the same fundamental class. Okay, I didn't write the details, but that is of course such example. And of course, you know, that's not, I mean, these were just finite dimensional examples, so that we're aware of it. Where we're interested in really is our Gromov-Witten theory. Another simple example, I mean, another well, infinite dimensional example, it's what's called the Uhlenbeck compactification of the Donaldson moduli space. It actually appears in some old paper of Donaldson and Kronheimer, where actually they also use Steroid Homology. What's important in this kind of setup is that you know, the singular locus that you're added, you don't really need the Color theorem, right? So you just need to know that it's homologically codimension true, but it can fit in as badly as possible. You still get this fundamental class in Steroid to begin with, but then if you extend it by continuity in Cech homology, and so the Uhlenbeck compactification of Donaldson moduli space is such a thin family, so that it's over the space of metrics in that case, and so you get a virtual fundamental class for every single metric. And of course, our main example is our main interest is what's called the stable map compactification in Gromov-Witten theory over say, for example, the space of almost complex structures, or maybe some sort of perturbations, domain-dependent perturbations. What happens in that case is that, I mean, in general, you cannot always show this is a thin compactification, because you would need to know that you've got enough transversality, so the boundary is codimension too. But there are some special cases where this happens. For example, if all the domains are stable, then as we know, if you turn on Rouen-Tian perturbations, these are domain-dependent perturbations, then the stable map compactification over the space of Rouen-Tian perturbations is actually a thin compactification. And so in particular, you get a fundamental class for every single Rouen-Tian parameter, and in particular for every single almost complex structure J compatible with omega. You get a virtual fundamental class in the Cech homology of that fiber of that particular modular space, no matter how bad the modular space is. Another, you know, slightly more general, if you knew, for example, that C1 of A, C1 on the C1 of A is at least 2 on all unstable domain J holomorphic spheres, then this is still going to work. The stable map compactification is still thin, because even though you may see multiple covers, you can still cover that multiple cover stratum by codimension 2 manifolds, so that's still thin. And there is a standard assumption that if X is semi-positive, I'm not going to give the precise definition, but there is a condition that if X is semi-positive, then in that case, there is there is a different construction, a smaller compactification, what's called the reduced compactification, it's also thin. And of course, this extends to many other setups. It also extends not just to the usual stable map compactification, but also it extends to relative moduli spaces, relative divisor, where in that case, especially once you start allowing divisors to have singularities like normal coursing singularities, there are in fact several natural compactifications in that setup. And the point, one of our main interest in this project was, how do we know we get the same invariants? Well, it turns out that even though there are all these many different natural compactifications, as long as all of them have boundary codimension 2, in other words, as long as all of them are thin, then you really get the same virtual fundamental class. So that was one of our motivations. Do you have, are there any questions so far? All right, so these are our main properties. So let's see. So as I said, our main interest was in the stable map compactification. And so far, as you can see, we basically, we get such a thin family, and in particular, such a virtual fundamental class, only in some special situations. However, one can extend it more generally using the properties of this, basically using topological arguments. So, let me start with some of the simple properties. First of all, as I mentioned earlier, the codimension 2 stuff doesn't matter. Okay, so it doesn't really matter how this codimension, as long as this singular set we added is closed, and it's also homologically codimension 2, then it doesn't really matter how it fits in. So you actually don't need any gluing or any Kohler theorem away from codimension 2. Okay? However, if you have some codimension 1 strata in your arguments, then you still need to do gluing. In other words, you still need to know that your space, your moduli space, is a manifold across this codimension 1 strata, or maybe it's a manifold with boundary, or if you had codimension 1 strata. So the example, recently we used this type of arguments in joint work with Penka Georgieva. I should have said this for what are called real Gromov-Witten invariants. So these are Gromov-Witten invariants in the presence of complex conjugation or anti-symplectic involution. You count maps which are invariant under this involution. And in that situation, you actually do have real codimension 1 strata. And you do need, in order to apply this kind of arguments, you do need to glue across this real codimension 1 strata to get a manifold, to show that the moduli space is topologically a manifold across this codimension 1 strata, but still codimension 2 strata, for example, where you have more nodes, or if you work with a real, we for example, use this type of arguments to get a splitting formula for the contribution of multiple covers of curves in a Calabi-Yau threefold, real Calabi-Yau threefold. So for those kind of purposes, these kind of conditions were satisfied, and so this was enough to work just on the top stratum, and also on the codimension 1 strata, but not the other strata. The rest of the strata were codimension 2 or more, and we just needed to know their codimension 2 or more. We didn't need to know any gluing or any kind of local normal how the moduli space looked normally to the strata. Okay? And of course, I added here just as an observation. If when you added codimension, if you added boundary strata which are more than codimension 0, then you are completely out of luck. So this method doesn't work always, right? You just need to make sure that whichever way you compactify, you want to make sure that the boundary strata are codimension 2 or more, and usually that requires some construction, and of course requires that you have some amount of transversality, because how else are you going to show that the boundary strata are codimension 2 or more? Well, I gave you the simple criteria, but usually that follows using some amount of transversality. Okay. And let's see, and then so it's. I'm not sure if my talk is supposed to be 40 minutes or 50 minutes. I think 40 minutes, but I have one more slide if you want. And that is, as I said, the properties of this, what are the properties of this virtual fundamental, relative fundamental classes that allows us, in fact, to extend. There are various tricks one can play where one can extend, one can start with a setup here, where we have a table map compactification under some assumptions, special assumptions, and then using properties of this families of these fundamental classes, one can then extend it more generally. So what are these properties? So here are some very useful properties of these fundamental classes. So first of all, I'll start again with one. So this is not with family. So this, if we have a map, a continuous map, all my maps are continuous, a degree D map between two topological manifolds. So these again are Hausdorff manifolds, are not necessarily compact, okay? But you can talk about what it means to be a degree D map, for example, in steroid homology. Or if you want, if these are smooth manifolds, you can look at the generic fiber having D points when counted with sign. But anyway, if you have a degree D map between two topological manifolds, if you know that this extends continuously to a thin, as a continuous map between two thin compactifications, then in fact, the push forward of one fundamental class is D times the push forward of the other fundamental. The push forward of the fundamental class of the domain is D times the fundamental class of the target. And so if you want, as a corollary, you can apply this to the identity map in two different compactifications of the same manifold, or to things like branch covers or Ward singularities. So here I have some schematic picture where I have these two manifolds M and N, and I've got the covering if you want. It doesn't have to be, if you want, you can also apply it for a topological covering. If you have a topological covering between these two manifolds away from codimension 2, from a codimension 2 set here and a codimension 2 set here, then the fundamental class here pushes forward to D times the fundamental class here. So again, to some extent, exactly how you compactify, I mean, you can also think that here, I mean, again, depending on your situation, there could be another compactification where maybe here, instead of compactifying by adding 1 point, you could have added several points, right? You could have, I mean, again, depending what your topological, but there may have been a compactification, maybe that look like that, right? Then that also, and if your map extended there, then also you have a fundamental class over here. And then a fundamental, oops, again, it stopped sharing. Oh, do you still see it? Oh, yeah, okay.
Yeah.
Like you've got the fundamental class here. It also pushes forward to a fundamental class here. So that's one of the, the simple properties. The second, the more importantly, as I said earlier, this construction is compatible with Pardon's construction of the virtual fundamental class using implicit atlases. So Pardon's construction is more general, but of course, just like singular homology, it's a bit hard to calculate anything from the definition. So in particular, I didn't write down what it means is compatibility, but in particular, if you know that you have something which is if you have a moduli space, which on one hand, it's a thin compactification of something, and on the other hand, that it has an implicit atlas, then the two fundamental classes are actually the same. So that's basically, what it means, the compatibility. What does it mean are the same? To be specific, Pardon's constructs his fundamental class in the dual to Cech homology. We constructed in Cech homology, so I guess. But if you work with few coefficients, those two groups are naturally isomorphic, or otherwise you have a map from Cech homology to the dual to Cech homology, and the two classes agree under this image. So that's one of the properties, and it's also compatible. So the properties that allow you, it's also compatible with pseudo-cycles and cut-down moduli spaces. So here I try to give this. A simple description of that. Let's assume that we have a map from such a family M bar. So for me, M bar, it's always a family over some parameter space. And here's a picture of it. It's such a thinly compactified family over a parameter space. And let's assume we have a map F to a smooth manifold, say. And for simplicity, let's assume that this family that we have here, this compactification, is stratified with boundary of codimension 2. And let's also assume that F restricted to each strata, it's a Fredholm map. Okay, so we have Fredholm maps between separable Banach manifolds, so each strata is a separable Banach manifold, and the whole thing is being compactified, so this projection is proper and continuous. Okay, so under this situation, then you can show that the generic, I should have said this, for generic P, the image of the generic fiber, it's actually a pseudo-cycle. Okay. And not only that, but the push forward of this virtual fundamental cycle constructed, right? So the generic fiber has, not only the generic fiber, but every fiber has this virtual fundamental cycle. And then the push forward of this virtual fundamental cycle is the same as the cycle, I mean, the homology class associated to the image when you regard it as a pseudo-cycle. Okay, so that's what I mean by compatible with the pseudo-cycle. This is the push forward of a homology, if you want a Cech homology class, but here the equality is happening in the homology of a smooth manifold, and for a smooth manifold, all these homologies are the same. As I've said, it's called smooth compact, I guess, if you want. I mean, it doesn't matter. Maybe it does. Okay, let's make it compact. Right, smooth compact manifold. And then secondly, furthermore, if moreover we know that inside N we have some submanifold Y, let's say smooth submanifold Y, and we know that this map is transverse to this submanifold, which means it's strata-wise transverse, right? So remember, this moduli space is stratified, so this just means that the restriction of this map to every single stratum is transverse to Y. Then the inverse image, I didn't draw the picture, but the inverse image here is going to be some thin family, thinly compactified family. And furthermore, its homology, its virtual fundamental class, okay, for this family is going to be the virtual fundamental class of the original family, cap with a Tom class. Okay, so this is an equality. Let me just say, maybe this is too technical, but it's a very important point. So this is an equality. This is an equality in the homology of the fiber of this smaller family, of this cut down moduli space. Usually this is done, for example, in Gromov-Witten theory. You use the evaluation map and you cut down by some constraints. Evaluation or stabilization map, you cut down by some constraints. So this is actually an equality in the homology of that cut down moduli space. And I should have said what this tau is. What tau is, it's what's called the localized Tom class of this submanifold. So it's a Cech homology class on the ambient space relative the complement, right? So it's localized on Y. And so this is an equality localized on Y. And using this kind of properties, in fact, one can extend. This is still work in progress. It's not completely finalized. It's not completely written down. But using this kind of property, one can actually extend the definition of virtual fundamental class for, say, for a stable map compactification beyond the assumptions, beyond this situation that I gave you here to a more general case by starting with the moduli space and modifying the problem to get ourselves into a case where this is satisfied, and then using this kind of properties to go back to the case we're interested in. So maybe I'll stop here, and I guess I'm out of time.